Welcome to the Straight and Level Briefing. Let's get started by looking at some revision. It's important you've watched the previous lesson and learned the main outcomes. Here's a quick quiz to make sure you are ready to carry on. Name the airplane primary controls, describe their location and their function. Now, state the three axes of movement. Can you name the four forces that act on an airplane in flight? Now can you name the 5 factors that affect lift production? And can you name the 6 ancillary controls and state their function? It's important you have this knowledge, as carrying on if you don't will just cause more misunderstanding. If you missed answering one or more of these, go back and review the previous lessons. If you answered all of these questions correctly, well done. And let's get started on straight and level flight. Let's look at some basic definitions as we'll use them. Straight, this is referring to a constant heading. Level, this is in relation to a constant altitude. Both of these can be seen here. So straight and level exists when the airplane is being flown in balanced flight, maintaining a constant altitude and heading at a steady airspeed. As always, here are the outcomes we want to achieve from this lesson. By the end of this brief, you will be able to state the forces which must be in equilibrium to maintain a constant height and speed in level flight. List the actions and checks required to establish straight and level flight. And with reference to the total drag graph, explain why thrust required for level flight is minimized at medium airspeeds, and it increases at high and low airspeeds. While this lesson and flying straight and level sounds easy, it is far from that in practice. Many a promising pilot has been beaten by not being able to perform this action correctly. Being able to fly straight and level will be something that will either make the workload lower and allow you to perform other duties, or it will take all of your attention and make it harder to do things like navigate, fly instrument approach, all kinds of other more advanced procedures. Practice does not make perfect. Only perfect practice makes perfect. So the time you put into this lesson, and then applying it in practice, will pay off in the long term. So let's get started. When we are in steady straight and level flight, the forces around the airplane are in a state of equilibrium to maintain a constant heading, height, and airspeed. Therefore, when we are in straight and level flight, lift is equal to weight, and thrust is equal to drag. As always, let's correctly define what we're talking about. We said that to achieve straight and level flight, we must have the airplane in a state of equilibrium. Let's make sure we are using the correct definition of equilibrium to avoid unnecessary confusion. Equilibrium means a state in which opposing forces or influences are balanced. In its most basic form, from its Latin origin, it means equal. Now that we are sure of what we are discussing, let's look again at the 4 forces that act upon an airplane in flight. We have lift, acting upwards. Opposing that, is weight, acting earthward. Thrust, is acting forward. Drag, is acting rearward. These forces are designed by our friendly engineers to work in certain ways together. To really understand this, let's look at another word, which is a couple. A couple, for our interest, is a pair of equal and parallel forces, acting in opposite directions, and tending to cause rotation about an axis. It acts perpendicular, which is to say at 90 degrees, to the plane controlling them. A plane is a straight line, along which a force acts. We have lift and weight, which are equal and parallel forces. They tend to cause rotation around the lateral axis. This is at 90 degrees to the plane containing them, which is the normal axis. You can see from the diagram that lift and weight are joined, and when either are increased or decreased in strength, it will have a direct effect on the other. It's almost impossible to increase weight in flight, but when lift is increased, it will have the effect of pitching the nose down. This is counteracted through different means when the airplane is being designed. Imagine the airplane is starting to take off down the runway. The lift is increasing and the nose starts pointing upwards. The faster it goes, the more lift it creates, and the more the nose pitches up. This would create the effect of the nose continuing to pitch up as it gets faster, either on takeoff or in flight. Remembering back to the production of lift, when the nose is pitched up, the angle of attack is increased. The increase in angle of attack creates more lift. This pitches the nose up again, and you can see we would end up over pitching and stalling the airplane. So an airplane has been designed and engineered to have a couple that pitches the nose down when weight or lift are increased. Now, we also have another two forces which affect the pitch couple of the airplane. That is thrust and drag. You can see from this diagram that thrust and drag couple together. When either are increased, this time it increases the pitch up couple. However, this is a much lower force than the lift and weight couple. I mentioned before that there are things done to counteract these couples. And as you can see, this airplane in flight would continue to pitch down due to the much higher pitch down couple. As an important note, you can see that all four of these forces are set up to act around a central point. Going back to these two couples, we still need to find how we are going to compensate for the lower thrust and drag couple. By definition, we need equilibrium to make an airplane fly straight and level. To answer this question, the force we use to balance these forces is by the tail-down force. This is achieved by the elevator and the horizontal stabilizer. The tail-down force adds to the weight that the wings support. It essentially is adding weight to the airplane in flight. Another important point is that the tail-down force is acting around the same axis the other forces are acting through. Because the tail-down force is further away from the center of forces than the other four forces, it has more effect due to the moment of the tail. That is to say, the tail is further away, so it produces a larger twisting force. We mentioned in the effects of controls that if you increase power, the nose will pitch up and to the left. This couple explains why it pitches up. So if you are flying straight and level, and you add power, the nose will pitch up. Likewise, reducing power will make it pitch down. Another benefit of this setup is that if you suffer an engine failure, the reduction in thrust will pitch the nose down, which will maintain the airspeed. Let's look at drag, as it is one of the four forces that act on an airplane. Drag is defined as something which impedes progress. And that's exactly what it does in flight. Drag at the top end of the spectrum would be letting a parachute out behind your airplane. Although there are some airplanes that used to use this system to slow down after landing, it is quite evident that this would not help you fly. There are several different types of drag. They can be organized into different branches of drag, in what is known as the drag tree. The total drag is the culmination of all of the different types of drag together. On one side of the tree, we have what's known as parasite drag. Parasite drag is caused by friction between the air and the aircraft's surface, aerials, the landing gear, etc. Form drag results as fluid flows over a body. The shape of the body determines the amount of turbulence that is created. The amount of turbulence is proportional to the amount of drag. So from this, we can see that turbulence is drag and vice versa. Turbulence is defined as a condition of fluid flow in which the flow is not smooth. The velocity, the speed and direction of the flow changes rapidly, and the flow direction often reverses. Let's look at this in practice. Potentially, the most non-aerodynamic surface would be a brick wall. You can see here that the air flows smoothly until it reaches the wall. At that point, it is not smooth. It changes velocity quickly and sometimes reverses. If we were to change the surface to something more aerodynamic, we can see that there is less turbulence. However, there is still turbulence at the other end of the airflow, and this creates the drag. The air colliding with the ball is going to be of a higher pressure from the impacting the ball. The air on the right side of the ball would be a lower pressure due to the separation of the air. This lower pressure has the effect of pulling the ball away from the airflow, slowing it down. If we take the ball and lessen the impact with the air, by creating a lower angle of impact, the air flows much more smoothly over the ball. This reduces the drag. This type of drag is called form drag, as it is created by the actual form of the object. The next type of drag to fall under parasite drag is skin friction. Microscopic imperfections on the surface cause tiny turbulent air pockets. Laminar means smooth and without turbulence. When the paint gets old and rough, you get bugs on the paint, or there are small dents and scratches, there is less laminar flow. Under the heading of parasite drag is also interference drag. This is drag formed at the junction of various surfaces. This occurs anywhere there are sharp angles joining. The air is forced into the angle, where it mixes with air coming from the other side of the angle. When they mix, they create a swirling and turbulence. This also creates drag. We can graph the drag that is created to give us a visible display of the drag. When we look at the drag and the airspeed, we can see that as airspeed increases, parasite drag increases. Let's look at the other side of the tree. There, we have induced drag. Induced drag is a byproduct of lift. So therefore, when angle of attack is increased, the wing extracts more lift from a given airflow. Lift increased in this way results in an increase in induced drag. But what is induced drag? To answer that, take a wing, and let's look at the pressure differences around that wing. On the top of the wing, we obviously have a lower pressure. That is our lift. Underneath the wing, we have a higher pressure. Air always wants to fill a vacuum, or in other words, air will always want to travel from a higher pressure to a lower pressure. This is a natural way of creating balance. So the air underneath the wing will travel to the sides of the wing, where it spills over into the low pressure system above. When the higher pressure air spills into the lower pressure, it increases the pressure. This reduces the lift being made, as the low pressure area above is now not as low. It also creates vortices, which are swirling tunnels of air. When the air swirls together, its velocity changes. And as you now know, that creates drag. So by introducing winglets, engineers are able to slow the mixing of air, and keep more higher pressure air from escaping into the lower pressure. They also minimize the size of the swirls, which reduces drag. That's why we've seen such a focus on winglets over the past couple of decades. By using winglets to reduce wing tip vortices, it's possible to save 45,000 gallons of fuel a year from just one plane. Next, let's look at downwash. Downwash is the air that is deflected perpendicular to the direction of the airfoil. You can see this effect by placing a spoon under the flow of a kitchen tap. The water will curve around the spoon, and continue to curve after it leaves the spoon. Fun fact. As the actual airflow is being curved downwards at the rear, the actual relative airflow is considered to be curved downward as well. As lift is always perpendicular to the relative airflow, it is actually bent backwards towards the rear of the airplane. As it now has the effect of not just pulling upwards, but slightly backwards, it is producing some drag. We can also graph the induced drag next to the parasite drag on our drag graph. It shows us an interesting phenomena. It shows that induced drag is higher at low airspeeds. And it shows that parasite drag is higher at higher airspeeds. Together, these two types of drag give what's known as the total drag curve. Or just, the drag curve. You can see that in the middle, drag is actually less. This is used to our advantage, and a lot of work goes into discovering where the optimum areas of least drag are. So having a thorough understanding of this subject is very beneficial for a pilot. There's much more to learn on this subject. Thrust acts forward of the power plant, to pull, or push the airplane forward. In level flight, only thrust is available to overcome drag. So thrust will always act forward, along the axis of the power plant. The definition of thrust is the forward aerodynamic force, produced by a propeller and other means, that forces a mass of air to the rear, behind the airplane. So we said that only thrust is available to overcome drag. When we take the drag curve, we can change it to be thrust required. This is all that is required to overcome drag, and therefore to have the airplane fly. This is why there is an equilibrium of forces in straight and level. We need enough thrust to overcome drag, to make us fly straight and level. The thrust available is always different. Thrust available is dependent on the horsepower available and the propeller. When we add this to the graph, we can see there is excess thrust available. So based on airspeed, there is a certain amount of thrust that is required to overcome drag. Any more thrust is excess. And you can see that level flight is available between the points on the graph, where there is thrust equal to, or in excess of, the total drag. Level flight is available between these speeds. At low speeds, there isn't enough lift to get airborne, and at higher speeds, the power plant isn't strong enough to overcome the drag. Let's look at stability. It's the natural, or built-in tendency, for an object returned to its original attitude, or position, once disturbed from that attitude or position. So, is stability good or bad? That's a very debatable question. Let's take a further look at stability, and you can make up your own mind. There are several types of stability. Negative stability is the tendency for an object to not return to its original position, once disturbed. Neutral stability is the tendency for an object to continue in the path that it was pushed. Positive stability is the tendency for an object to move to a stable position, after being moved or disrupted. An unstable airplane would move further from its original position after it got disrupted. A neutrally stable airplane would continue in the direction that it was disrupted. A stable airplane would return back to its original attitude, once disrupted. A stable airplane will recover its attitude after being upset by gusts or turbulent air. So the question is, which type of stability is better? You may have realized, it would depend on the type of operation as to which type of stability would be good. An airliner that wants passenger comfort would be more geared towards a positive stability. Whereas an aerobatic airplane would want a more neutral stability, so that it can be maneuvered as desired. Most airplanes use longitudinal dihedral to enhance pitch stability. Dihedral means a positive angle formed between two surfaces. This dihedral, or angle, is formed between the wing chord line and the horizontal stabilizer chord line. As we've seen, airflow over the wings is diverted downwards, called downwash, and therefore it changes the direction of the relative airflow on the tailplane. Most traditional light aircraft use a longitudinal dihedral to enhance stability. Airflow over the wings is diverted downwards, and therefore, changing the direction of the relative airflow on the tailplane. The horizontal stabilizer is rigged to enable level flight despite the downwash on the tailplane. So now we have two opposing forces. If the restoring influence caused by the tailplane is greater than the instability of the mainplane, then the airplane will be stable. What this means is that if the tailplane, also called the horizontal stabilizer, is applying more force than the main wing during a disruption, then the airplane will stabilize itself. This is because, if the airplane pitches up, it produces more lift. That will cause the downwash to have a lower angle of attack on the tailplane. The lower angle of attack will cause the tailplane to fly up, canceling out the mainplane's pitch up. Lateral stability involves the stability around the lateral axis. This does not mean it is pitching around the lateral axis. Instead, it is really pitching around the longitudinal axis, but is regarding stability around the lateral axis. To create stability, we can again use dihedral. Most light airplanes have a lateral dihedral, increasing stability in the roll, as we'll discuss now. As you can see in the diagram, with the horizon being represented by the green line, the wings are forming a positive angle, away from the horizon. The same as the longitudinal dihedral, this positive angle forms a dihedral. When encountering an uncommanded bank, due to a wind gust, it leads to a slip. Because of the dihedral, there is a larger angle on the downward wing. That larger angle creates a larger angle of attack, and therefore lift. More lift is created on the downward wing, and the wing is lifted. Helping with stability in the roll is the pendulum effect. High-wing aeroplanes rely less on dihedral, and more on the pendulum effect. You can see in the diagram, the airplane rolls to the left. Lift is acting upwards, and weight is acting downwards. Due to the concentration of lift and weight acting around certain points, the airplane is literally pulled into a level attitude. It's like a string going through the center of the airplane, and when you pull it tight, it will level out the wings. That just leaves us with directional stability to look at. An upset causing a yaw results in the tail fin having a positive angle of attack in relation to the relative airflow. This positive angle of attack results in the tail fin realigning with the airflow. So that's why they're called stabilizers. The vertical stabilizer will not only keep the tail stable on the normal axis in straight flight, but will also bring it back to stability if it's disrupted. Let's review this lesson and make sure you have a thorough understanding of the material. Remember that the number of times you review this material will equal how well you can understand and use it. So please, be patient, be humble, and be willing to go over things several times. You'll get more from it each time you do. What are the two types of drag? At what speed is drag the greatest? What is the purpose of a dihedral? For some added thinking. What types of airplanes would be designed to be unstable? What types of airplanes would be designed to be stable? So to summarize, in this brief, we looked at parasite drag, including skin friction, interference and form drag, increases with airspeed. Induced drag increases with lift, which is from the angle of attack, and it decreases with speed. Total drag is minimized at mid-range speeds. And we looked at stability in three planes: longitudinal, lateral and directional stability. Now, as an addition to this lesson, we can look at how to actually fly and maintain a straight and level flight. We will use a typical Cessna aircraft for the power settings. And we are going to use a common technique of flying straight and level. I want to introduce to you the saying that power and attitude equals performance. What is meant by this is that to maintain level flight, we need a power setting and an attitude which produce the correct amount of lift to stay level. Too much lift, and we climb. Too little lift, and we descend. So the saying is that power and attitude equals performance. First we set the power. Then we set and hold our attitude. You must know what attitude to set first. It's not a guessing game. For example, in the Cessna 172 you would set an attitude which is 4 fingers in height off the sun visor. So that means, there is 4 finger widths between the glare shield and the horizon. The next thing, once you have held the attitude for a couple of seconds, is to check the performance. In this case, our performance is maintaining level flight, and that can be checked off our altimeter. You can also check that the vertical speed indicator is reading 0. As discussed in the effects of controls lesson, this instrument has a lot of lag and is best used after holding the attitude and settling the airplane. Then, when you are maintaining or close to maintaining level flight, you can use the trim wheel to relieve the control pressure. This process may need to be done several times. As you change one thing, another thing is affected. So you will usually make a big change to set up for level flight, and then another or several smaller corrections until the airplane is comfortable in that configuration. To maintain level flight, you would check your power setting, attitude set, and trim is relieving the pressure, and then adjust any as required. As the air is hardly ever 100% smooth, you will constantly be correcting to maintain perfect level flight. To maintain straight flight, check your wings are level with the horizon. The balance ball is centered. And the performance is correct. In the case of flying straight, the performance is referring to the heading of the airplane. Here's the relationship of angle of attack to airspeed. This is possibly the most important relationship to good flight control of an airplane. This relationship exists from the smallest to the largest airplanes. If you can understand it and apply it well, from early on, you'll be well on your way to being a competent pilot. A misunderstanding, or not giving this relationship the correct importance, has been the ruin of many a student, and even advanced pilot. The relationship is simply, the higher a given airspeed being produced, the lower the angle of attack needed, to maintain level flight. The reverse is true also. The lower the airspeed, the higher the angle of attack required, to maintain level flight. The diagram on screen shows this. On the left side of the rectangle, it shows the upper triangle, which is angle of attack, is higher. The lower triangle, the airspeed, is lower. Move to the center of the rectangle, and both angle of attack and airspeed are equal. Move to the right of the rectangle, and the upper triangle, the angle of attack, is lower. The lower triangle, the airspeed, is higher. What we can take from this is that any change to airspeed requires a change to angle of attack to maintain level flight. And vice versa. Nothing you ever learn is valuable if you can't use it. Let's have a look at this in practice. An airplane flies along at a fast speed. The angle of attack required to maintain level flight is small. An airplane flies along at a slower speed. The angle of attack required to maintain level flight is larger. Anytime you disobey this rule, you will be creating less lift. Anytime you create less lift, you are unable to maintain level flight. Which is to say you will start to descend. Congratulations on getting this far. Let's summarize what we've discussed in this lesson. In this brief, we looked at parasite drag. This includes form and skin friction, as well as interference drag. This parasite drag increases with speed. We looked at induced drag. This is the drag produced by creating lift. Because of that, induced drag increases with an increase in angle of attack. From the total drag curve, we know that drag is lower at mid-range speeds. We looked at stability in all three planes. We had longitudinal, lateral, directional. We looked at how to establish and maintain straight and level flight. And we looked again at slow flight. This is the relationship of angle of attack to airspeed. Attitude must change when using flaps or changing speeds. If one wants to maintain level flight. This is because the change of speed and flaps, which we didn't speak about, changes the angle of attack. Let's check our outcomes were achieved. Number 1. State which forces must be in equilibrium to maintain height and speed in level flight. Number 2. List the actions and steps required to establish straight and level flight. Number 3. With reference to the total drag graph, explain why thrust required for level flight is minimized at medium speeds and increases for slow and fast flight. Finally, let's check that our understanding of drag is where it needs to be. What does this axis represent? What does this axis represent? What type of drag is this? What type of drag is this? And how is thrust related to this graph? Well done again. If you missed any of these answers, go back through the materials again and review it until you know it. These materials need to be known at a level of conceptual understanding, not just to pass an exam. As an instructor, you can always tell who knows this and who memorized it. Safe skies.